Hello, I hope all of you are doing fine. Now, in the earlier sessions or discussions, we have seen that we are designing any mechanical system with an intention to achieve some useful work, of course, but as well the intentions are that that system runs smoothly. So, in context of that, we have seen how unbalance gets created in a system, or the dynamic unbalance in a system is getting involved due to the inertia forces of the moving masses, and we have even tried to check them or control them or counter them, whatever these inertia forces are coming into the system, so that these mechanical systems operate smoothly. Now, apart from the inertia forces, there are as well other aspects also involved in a system which creates these kind of disturbances, and ultimately it's affecting to the smooth running of the system, or I can say that the system performs a non-smooth operation. So, to take care of this, again then there is one component called as a flywheel, which is again helping us to smoothen out the operation of any system. But before getting into the concept of how flywheel is or what the flywheel component is, we'll try to understand what is the background of this disturbance in a system. So, we have seen that for, if we consider, if I take this as a mechanical system, of course, now how does a mechanical system work? Now, we know that for a mechanical system we need some input, right, and this input is the power or the energy which we are supplying. So, this is the input power we are supplying. This power is getting utilized in the mechanical system, and then it gives the output or the work done, what we say useful work done. So, we get the output and or the output power, and some of these power, this power is lost into the friction or overcoming the inertia of the system and all. So, output plus power. So, the whole idea is that these two, the input and the output, this is supposed to be equal, because we know that energy cannot be destroyed nor be created. So, that is how a system works. Now, for example, if I take up a case, say there is a system, so with respect to time, if we try to understand, and say the power, fine. So, we are supplying, or there is an input power is this. So, we are supplying the power to the system, and say the output is, or the energy required by the mechanical system to do that work is this. So, maybe the output plus the losses. So, you can see the power which is delivered and power which is required, there is a mismatch kind of a thing. So, maybe the required power is, or the required energy is lesser than what we are supplying. Now, as I have said, energy cannot be created nor be destroyed. So, that means where this energy will go? This energy will remain in the system, and eventually it will, as this is a mechanical system. So, the energy what we are talking about is mechanical energy. That means when this energy remains in the system, so the system energy or the system kinetic energy will gradually increase. So, with respect to time, again, if we try to plot a graph between the time and the speed. So you will see that eventually the speed of the operation is going to increase, right? So this is quite obvious. As we can see, the energy is getting stored in the system, and of course it is in the form of kinetic energy, so the speed of the system is going to increase. Now this I can call as a case 1. There can be another case where, say, again if we plot a graph between the power and time, say this is the input power which we are supplying, but what is happening is the required power or required energy of operation is maybe greater than what we are supplying. So this is the output power plus the losses. So that means we can see that the operation needs more power than, or more energy than what we are supplying. So due to the inertia, the power available in the system, due to the inertia of the mechanical system, that power or energy will be utilized. But again, eventually we will see that there will be always a deficit of power in the system. So the energy of the system will drop. So when this energy of system is dropping, so now if we see the relation of speed, what will happen to the speed of operation in due course of time, we will see that it is going to reduce. Now these are very typical situations I am talking about. Like I can say that this is a start of an engine, wherein initially the start of a mechanical system, when we are starting a mechanical system, the initial velocity will be 0, right, and we are pumping in more energy. So gradually the speed of the system is getting increased, and reaching to maybe at a steady state level. So that we will see how. The second case can be a stopping of a system. So when we are killing the input energy, so that means the operation speed is going to gradually reduce because the supply of energy is reduced, or there is no supply of energy. So whatever inertia is available, so whatever kinetic energy is available in that mechanical system, that is getting utilized, and gradually the speed will drop, the operation speed will drop. Now the objective of this is to understand is that I need to have a steady operational speed. But if we see typically, or actually if you see, these are the two cases we were talking about. So as we have seen, there is a straight line, but it will not be absolutely a straight line, but rather there will be some fluctuation. So maybe this is the increase in speed if the energy is remaining in the system, and this is the decrease in the operation speed when the supply of input is lesser than what is required, and what we expect is a steady operation. So somewhat like this. So I need to have this as a steady operational speed. So this is what is expected. So when this is happening, then only I can say that the system is running smoothly. Now when this can happen? Now this can happen only when, let us say, whatever input I am supplying, when this input supplied is same as that of, so when there is no mismatch, as we were seeing that when the input power is more then the required or the operation required energy required for the operation, the speed was increasing. When the supply of energy is less than the energy required for the operation, then the speed was decreasing because there is a deficit. So in that case, what we need for a system is that if this is the input, the power supplied and power utilized, when these two are same, so this is the input and this is the output plus the losses what we are talking. So when they are matching, when they are same, at that time we will definitely get, or it is expected that we get the operation speed to be, say, in that case we will get with respect to time the operation speed to be a steady state. So this is what is expected. But actually if we see a system, this is not going to happen or this does not happen, then the question is why or how this does not happen. Now if I am talking about a mechanical system, the requirement of the energy at different stages or during the cycle can be different. For example, if I say a punching press, so you can see that during a cycle it does not require energy at every situation of the cycle, because during one cycle maybe 1 or 2 punches it is doing, or if it is a riveting machine, so that is happening. So maybe 3 or 4 riveting it is doing. So energy is required only during the time of that actual operation when it is taking place, and rest of the cycle there is no need of the energy. That means the requirement is fluctuating. In the other hand, if I talk about an engine, so if we say an engine, it is having different 4 strokes. So during all the 4 strokes, the delivery torque or the energy delivered will not be same. During suction, the system requires or needs energy. So the energy is delivered only during the power stroke. So that means the input and output both are fluctuating, right? So what is the objective then in that case? That means what we try to match here, when I say the input power is equal to the output power, that means during the cycle whatever is the average power delivered must be equal to the average power consumed. So when these two are same, so we can say that the input and output conditions, they are matching. So that is how we can, so that should give us maybe a steady speed, but this steady speed what we are getting is the average speed of the operation, the speed of the operation, right? So that means during the cycle we get these averages to be same. But if we see the instantaneous conditions, there are chances that they are varying, as I have just now said that the requirements can be different. So how this may happen? So let us see that so if we plot a graph with respect to time, or maybe this is the cycle time, I can say, maybe for one cycle we are talking, and this is the energy or power we are talking about, what we are supplying and utilizing. So when we are comparing, so maybe say this is the input, so this is the input what we are supplying, and say this is what is maybe the output. So these are the two curves. So input is fluctuating and this is the operation. This is how output plus losses. So this is how, say, for this is one cycle, this is what is happening, and say the average value. So when we so this is the average value of energy for, so what is the average? The average for both input and output to be the same. So when this is same, so it is expected that the average speed is constant or steady. Now the average speed is steady, but now if we see the instantaneous conditions in this case, though the input supplied and output, they are same, their averages when we are counting, they are same. So but during the cycle, if we see, these are the two positions where these two graphs are, or these two are intersecting. So at these two positions we can see, so here now if we compare or see for the cycle time, and speed. So when we are comparing, so there is intersection here. So at these two positions we can see that the operational speed is equal to the input speed. But what about this situation? So here maybe if you see at this portion, the input is more than the output what is utilized. So maybe that is say this is that speed. Now here, from here to here, from this cycle position to this position of cycle, you will see that the input is less than the output, or the supply of energy is lesser than what is required. That means from this position to this position, the speed is going to drop, right? So it is, maybe it is dropping this way. So the speed drops, and from here, from this point onwards, again you can see that the input is more than the required energy. So gradually the speed is going to increase. So maybe this is how we will get the curve for speed. So we can see, even though the average energy of both the input and output, they are same, but there will be a fluctuation of speed during the cycle. So if there is this fluctuation existing in the system, and we are talking about mechanical energy, that means there is variation or there is fluctuation of energy during the cycle, and this fluctuation will affect into the non-smooth running of the operation. So now our job is to see how we can smoothen out this fluctuation of energy so that the operation becomes smoother. So there is this component called as the flywheel, which is helping us to manage this fluctuation of energy. So and we will see how it is going to help us. So if we see now, when we are talking about the power, so let's see this. So as we have seen just now, the operational speed comes out to be fluctuating. Now there can be cases wherein just now, as I have or we have seen, that when the input is varying as well as the output is varying. But in general, if we see in our mechanical systems, like we have situations when, say, the input is varying and the output, say this is the output and the output is constant. So this input is varying and the output is constant. So it can be a case of, like, say I am using an engine to run a generator. So the load, I can say the load of the generator or speed of the generator required is constant. So the load is constant on the generator, but engine will be producing the energy which will be varying during the cycle. So the input is varying and the output is constant. Second situation typically can be where the input is constant and say the output is varying. So this is the output. So the output is varying. So in this case, we can say that as if we are running any machine tool or a machine like punching press or a riveting machine or anything with the help of a motor. So when the supply is constant, so the supply is constant and the requirement of energy is varying. So typically these can be three situations. So when we say this output or input to be constant, that means the load is varying and the supply is constant. So when this is constant, so as if then this value or the input energy or the input torque is constant, or this will be equal to the average torque of the condition, and here the load is constant. So this constant value will be equal to the average torque or average energy required. So these are the two cases, and the first one which we have discussed, where input is varying with as well as the output is varying. That means maybe I am running a machine with the help of an engine where the input is also fluctuating and the output is also fluctuating. So now if you see, it's very important to understand then how this energy condition or the power is varying during the cycle. Now for that, it is very important to understand the turning moment diagram, or the what we call as the T theta diagram, wherein why it is important is because typically if we see the turning moment, that means the torque or the moment, this is of course function of theta, where theta is the crank angle. Now if we see the graph between, so this is the crank angle theta and this is the torque we are talking about. So, for example, if I take the turning movement diagram of a 4-stroke engine, so this is torque, which is function of theta, and this is crank angle theta, so pi So, a very typical, if you see the variation of the torque during the cycle, you will see that it is varying substantially. So, there is a lot of variation, and say this is the average torque. So, what I am saying, this is the average torque of this cycle. Now, if we talk about the energy, so what is the energy during this cycle? Let us say it is E. Now, this is the torque. So, here we are talking about the mechanical energy, that means kinetic energy. So, it is the force into displacement. So, this is the torque, it is the applied force, and displacement is theta of the crank. So, if I take a very infinitesimally small d theta, so I can say that this torque into this small area will be the work done. So, for the entire cycle, that means it is the area under this curve, which is so that means it is, which is function of theta into d theta, right? And for a cycle, so for complete cycle, it will be the energy, that is area under this curve. So, right. Now, that means what? So, this average torque into 0 to 4 pi, this energy, that means this area is equal to area under this entire curve, when we say, when we are matching the input and output conditions, right. Now, typically then, for if this is a I have considered a 4-stroke cycle or IC engine, then energy required for this is 0 to 4 pi d theta. This is for a 4-stroke IC engine, and if it is a 2-stroke engine, then it will be 0 to 2 pi t d theta. This is for 2-stroke IC engine, or you can say a steam engine. Then what should be the average torque? This average torque, I can say that the average torque will be equal to E upon, if it is a 4-stroke engine, it will be by 4 pi. So, this is for 4-stroke IC engine, and average torque we can determine it will be E upon 2 pi. So this is equal to 1 upon 4 pi 0 to 4 pi T d theta for a 4-stroke engine, and this will be 1 upon 2 pi, so 0 to 2 pi tau d theta for a 2-stroke engine. So that is how it will be. Now let us try to understand how this energy is fluctuating in the system. So let's see how this energy is varying during the entire cycle, so that we can understand what is the fluctuation of the energy in the system. So for that, say, let us say this is this intersection is point A, say this is point B, this is C, this is D, and say this is E. Now let I say that, say the energy at A is EA. So at this position, the energy at, right now, you can see, compared to the average condition, the supply of energy is more than the average value. So that means there is excess of energy in the system. So I'll take this, or we consider this loop as positive. Now here from B to C, you see that the driving torque is less than the average torque. So that means there is deficit of energy, you can say. So I take this as a negative loop in the system. So this is from, so this is the suction stroke, this is the compression stroke. Now this is the working stroke or the power stroke. So say this is positive, so the input or the driving torque is greater than the average torque, and again during the exhaust stroke there is a negative loop achieved, and here again this is positive till A, you can say. So this is how the variation of the torque is in the entire system. So let us say the energy at A is EA, then what will be the energy at B? So this energy at B will be this smaller loop. That means if you see area under, from say this is theta A, this is theta B. So what is the energy, excess energy available in the system? It will be this area minus this area. So it is, this will give us what is the energy available at B, which is definitely a positive value and greater than. So you can say it will be energy at, so energy at B will be energy at A plus it will be the area under, so from theta A to theta B, and it will be torque available minus the average torque d theta. So this is the energy available at B. So what will be energy available at C? So energy available at C will be, again it is area under this curve minus area under this curve. Now of course this value is, so it will be energy at B plus, so it will be from theta B to theta C. So theta B to theta C, again it will be the available torque minus the average torque d theta, and of course this value will be negative. So eventually we will get this energy to be as a negative value when we take the summation. So, what is energy at D? Energy at D will be energy at C plus the area under this curve. So, this is the energy which is available at D. So, it will be from theta C to theta D, where this is the torque which is function of theta minus the average torque. So, we get this as energy at D. Again, energy at E is equal to, I can say, energy at D plus theta D to theta E, where the torque is function. So, equation of torque will be a function of theta. So, minus that. So, I can get this value. So, again now we come back to energy at A. So, energy at A will be energy at E plus, so from theta E to theta D. So, energy at A will be energy at E. So, from theta D to theta A. So, which will be equal to this value. So, that is how we can find out the energies available during the cycle, right. Now, when we are finding out this, so this all these values of the energies will be different at all these conditions. There has to be some value which is maximum, right, out of this EA, B, C, D, E and EA. Again, if we see, out of this any one value will be a maximum value, right, and one value will be, out of this will be the minimum value. So, that means the difference of this maximum value to the minimum value will be the maximum fluctuation in the energy. So, in that case, say out of these, say any one. So, here I can see maximum portion is this. So, maybe this C to D energy at D, this is the maximum value, let us say. So, if this is maximum and somewhere here if this is the minimum, so the difference of these two will give me the maximum fluctuation of energy, which is of course the mechanical energy or kinetic energy. So, we can write that as, we denote it as delta K max. So, what is this delta K max? It is the maximum fluctuation of energy. So, let us see that. So, maximum fluctuation of energy is denoted as the delta K max, which will be equal to the maximum energy during the cycle minus the minimum energy during the cycle. Or I can say that, say this is from theta max to theta minimum. If this is, these are the two conditions of the theta. So, we can say this to be as E max or minus P average from theta of maximum value, theta minimum, d theta. So, this will be the maximum fluctuation of energy. Now, there is another term Now if there is another term, or if we see that this delta Ke max divided by the work done during the cycle, during the entire cycle, so work done or per cycle, if I say, or the energy during the cycle, or E, if I say, this is called as Ke, which is coefficient of fluctuation of energy. So far we have seen this. Now this energy what we are talking about is the mechanical energy, it is the kinetic energy. Now this kinetic energy or can be also expressed as this, where this I is the moment of inertia of all the moving parts of the system which is there, which is rotating, and that can be equated to the condition of the energy available at that condition. Now when we say we are calculating the maximum fluctuation, so that means the maximum fluctuation of kinetic energy, we can say that it will be maximum when this omega is maximum. That means the instantaneous velocity condition at that time is maximum. So at that time or at that situation, the energy will be maximum and it will be minimum. Why we are saying this? Because we know that this delta Ke max, maximum fluctuation, will be E max minus E minimum. So this is the energy expression. So this will be maximum when the omega is maximum, and it will be minimum when the omega is minimum. So I can say this is half I omega square at minimum value. So we can say that, so the fluctuation of magnitude of this fluctuation of energy we can say as half I omega maximum square minus omega minimum square. So mathematically if we expand this situation, so we can say that right. So if we do so, then in that case we can say this omega max plus omega mean by 2, if we say, so this is the average value I can say. So I can say this is I omega average. So I am taking 2 here. So this becomes the average velocity into well and omega max minus omega minimum, and I multiply and divide this by the average value. If I do this just mathematically, so I get this as, so I am multiplying and dividing it by this value. So this is the average value. So we get this expression to be as I omega average square into now this value is called as the coefficient of fluctuation of speed. So this coefficient Ks, what we have got, which is equal to omega max minus omega mean by omega average, it is the coefficient of fluctuation of speed. So you can see the maximum fluctuation of speed, we get this expression to be as this, where this I, so that means you can see the maximum fluctuation of speed can be, if now they equated to a situation where mass rotating or a mass having this much mass moment of inertia in the system can, if we put, can take care or smoothen out this fluctuation, this much magnitude of energy, fluctuation of energy in the system. So we equate this, or we take this mass moment of inertia as the mass moment of inertia of the flywheel, which is rotating at the same average speed of as that of the system. So if I just put a mass of having this value in the same crankshaft, so that is more or less going to give me the fluctuation to be controlled, or more or less a smooth operation. So I can say that the mass of the flywheel, which I can determine, will be maximum fluctuation of energy so simply then I can put a mass of this much value in the system, which is going to more or less smoothen out the functioning or the operational speed of the system. So that is how we have understood what is the reason behind the occurrence of fluctuation of the energy in the system, and how we can determine this mass of the flywheel, and we can then more or less try to smoothen out the operation in any mechanical system, or we are in a position to create a match between the driving and the driven. So the energy delivered and consumed, so the variation in this, or the fluctuation on this speed, or rather we are talking about the instantaneous fluctuations during the cycle, so it is velocity. So we are smoothing out the velocity conditions for the given cycle. So that is all in this session.